This talk is about a project we did internally inside NetApp's Advanced Technology Group. Code name is SMORE, which is short for the SMR Object REpository. So a quick overview. I'm going to talk about a very brief overview of SMR. Everybody in this room probably already knows about this. Actually, put up your hand if you don't know about SMR. Okay, good. I can go really quick. Okay, then we're going to talk about the SMORE project. We're going to talk about some of the architectural elements that we considered relatively unique that may be of interest to the audience, some of our implementation results, lessons learned from the project, and then a little bit of time for questions and answers. Okay, so SMR is not a new technology. It's been around for, at least being discussed for over a decade. Originally, there were high hopes that this would allow over a doubling, but real-world performance has been more around 50% improvements. Ultimately, it's trading off flexibility for capacity, for density. And there's lots of SMR drives shipped. In fact, a lot of drives that don't say they're SMR, at least outwardly, are SMR technology under the covers. So this is a widely deployed technology that's used in many different areas. You may have an SMR drive and not even know about it. So how does SMR work? It's taking advantage of the fact that on conventional drives, there's these guard bands, these little gaps between the tracks where the data is laid down. These guard bands prevent writes from affecting adjacent tracks, but they take up space on the drive. So we want to put more data in there, let's overlap them. And so in short, SMR's shingling, overlapping tracks, taking advantage of the fact that a read head can be narrower than the write head, and allows you to pack in more data. So what's the trade-offs? Well, when you have overlap, if you try to go back and just rewrite data partway through these shingled tracks, you're going to clobber adjacent data. It's just geometry, it's physics. So as a result, SMR drives divide the drives into zones. Zones can be sequentially written to, randomly read from, and trimmed, i.e. your write pointer, where you're writing, gets set right back to the beginning and you can do it all over again. But you can't go in and change anything, you can't go in and delete, you can't move that write pointer back. So those are the limitations. So there's three types of SMR drives. Drive managed, where the drive hides the SMR complexity. Don't have to change any of your software, it just behaves differently, and sometimes that can cause unexpected behavior. Host managed, where the host is responsible for all the complexities of these SMR behaviors. And host aware, where you can do everything to make it work well on the host side, but if you make a mistake, the drive's going to kind of fix it for you, and hopefully everything should keep on working. So SMORE, our project here assumes host managed SMR. We manage all of the zones and write pointers, etc., in the software. So that's the context we're going to be talking about SMR in this presentation. So what is SMORE? It's a project from the Advanced Technology Group at NetApp. So the Advanced Technology Group is a division in the CTO's office in NetApp, charged with investigation of technology trends, exploration of changes in technology, in architecture and products available, and looking at where technology is going and how that can help our products from NetApp. So SMR being an emerging technology, i.e. at the time we were starting working at this, that was right when we were having large-scale availability and higher capacities available. Now, this was around the range when the 8 terabyte drives were starting to come out, and their roadmap for 10 terabyte, 12 terabyte, etc. So given that our view is that SMR drives are optimal for capacity storage and archives, we wanted to take a look at what the feasibility was for using SMR technology for archival storage products, and looking at the economics, performance envelope, use case, and full life cycle economics. So that was our mandate. And the way we do this typically is to build systems, because that's the best way to explore where things work well, where things don't work well, and learn about the gotchas. because the gotchas are always what make or break a product. And this is one of the big differences between academic research and industrial research, in that something that might be an interesting footnote or not even something that makes it into a conference paper is something that could make or break a product in a commercial environment. So one of the other things we wanted to do is we wanted to explore a number of novel ways to handle fault and error recovery strategies. And this became a platform for that. So after we had done the basic work of how do we make SMR drives into something that could be productized, we also spent a lot of time looking at fault and error recovery, because our experience managing a very large number of drives at customer sites and looking at resiliency, reliability data, we believe that going forward, as drive capacity continues to push the limits and they're used in archival workloads, being able to tolerate faults, strange faults, unexpected faults, concurrent faults is going to be, once again, very important for a company that wants to have a product that customers stand and say, yo, this just works. We're not losing data on it. None of our companies want to have products that become known for losing data, and as the components are not necessarily as reliable, you need to do additional error handling at different levels. So a more detailed report on this project is published at this address. We also presented some of our findings at FAST conference. So there's a lot more details available on this project if anyone here is interested in drilling down into that. Yes. Yeah. Okay, so let's jump into the actual project itself. So we made a number of assumptions at the beginning of the project. The first assumption being that, sorry, one second. There it is. Okay, first assumption is that architecturally, Flash is where you're going to put your hot data. And I don't think anyone here would question that assumption. The change in our customers' uptake in Flash has been immense, and that was a good decision. It was probably a little controversial at the time, back 2-3 years ago, but history has shown that the Flash transition has been faster than most people have expected, and that's been a good thing for most of our companies. Disk is for cool data, i.e. data where you need to be able to do seeks. And tape is for cold data. And the reason why I want to differentiate this is because tape has excellent economics if you extremely rarely read from it. And when you read from it, you read a majority of the data on a tape. And while this isn't part of this presentation, I just want to briefly share some findings from some research we did with some customers that were looking at large-scale tape archives. And when we did all the modeling, we found that if you have an object repository where you're even accessing a very few number of random objects per second, like in the range of, say, 10 objects per second, what ends up happening is you start to hit the tape wear characteristics long before the tape wear limitations, long before the typical lifespan of a tape for the economic modeling. So as a result of that, the customer would be having to buy new tapes on a fairly frequent basis and migrate data from old tapes that were wearing out because of the number of mount, unmount, seek cycles. And when you look at the total cost of ownership over even a 5-year period, disks were cheaper. If you look at a different workload, large chunks of data accessed infrequently, tape's the clear economic winner. So we believe that there's a clear kind of middle tier between Flash and tape for stuff that's cool, not cold, not hot. So the second thing that's really important to note is if all your hot data is being read out of Flash and cached in Flash, that means your accesses are essentially random. So it doesn't make sense to have any cache. It doesn't make sense to do any access locality. It's random. So that was the other assumption we made, and that influenced our architecture. And the other thing is that these workloads are primarily object-based. So once it gets down to the point where it's cool, you're not, this is the ideal data to go into an object repository. So we made an architectural decision that we were not going to make a file system, because a file system is substantially more work. It takes a lot longer to stabilize, and there's a lot more things that can go wrong. I'm making a basic object repository with the standard, put to write, get to delete, to retrieve, delete semantics. We were able to create a robust system in a fraction of the time it would have taken to create a whole new file system. And if we had proposed doing this 10 years ago, there would have been no traction. But because of S3 and the widespread adoption of S3, enterprise customers look at this and say, yeah, that's okay. We don't have a problem with that. There's a set of workloads that use these, these object type interfaces, and we understand that. And that's a big shift. And that's, I think, exciting for all of us, because it gives us a new kind of middle ground for building systems that doesn't necessarily have to have the full cost and complexity of POSIX or block. Okay, so one of our goals was to have streaming read and writes at the aggregate disk throughput. So even though this isn't what would typically be considered a high-performance workload, when you get into some of these big repositories, the amount of data going into them can be very high. So we set an internal goal. It was a stretch goal, but we actually achieved it, that if you take the theoretical maximum throughput of the individual drives and then you multiply that by the number of drives in the system, you'd be able to achieve that. And I'll show some results on this later in the presentation. This comes out of a number of, or I shouldn't say this comes out of a number of architectural decisions. We made a bunch of architectural decisions to try to achieve this, and we think that it worked quite well. So the other thing is that at the beginning of this, we had an architectural goal of, flash changes things. Even in systems that aren't flash storage, the judicious use of flash in your architecture can make different models possible that can simplify and save a lot of resources. So that's another thing we'll talk about. And we did everything user space. We didn't want to do anything in the kernel. Once again, complexity, etc. So those were our kind of assumptions and starting points. Here's how it looks like, the basic layer cake. It's a user level process that sits at the top. It's a SMORE process. It uses an NVRAM FIFO. We at NetApp love NVRAM. We did this for a number of reasons. The biggest reason is it lets us reliably collect up writes and then flush them down to disk in bulk. And this is really important for SMR drives because the direction is for the block size to get bigger and bigger and bigger. So if you're trying to do, 100 byte writes to SMR, you're not going to get anywhere near the performance. You need to get big writes and preferably block-aligned writes when you're sending data down. We used the user space SMR driver, the ZVC library. And we also had, so this is all for the array of collection, I shouldn't use the word array, but the set of SMR drives where the data was stored. We also included a flash device, and the flash device was used for the index. And I'll talk a little bit more about the index later on, but that was just a standard I/O process. We didn't do anything special on reading and writing to the index on the flash device. So, every object in an object repository has an identifier, and you need a way to translate between identifier and where your data is stored on these SMR disks, right? You've got different zones, you've got offsets within the zones, etc. You need a way to look that up. So once again, we didn't do anything too exotic here. We used a B+ tree. And as new objects are added, we add that to the B+ tree, and we keep the entire B+ tree in memory. And we periodically checkpoint that B+ tree out to the flash device. So during normal full write load operations, there's no traffic going to that flash device except when it checkpoints. And one of the reasons for this is we didn't want to be wearing out the device. One of the things you have to be careful of about flash is if you're having it where data is always going through your flash device, you can be putting a lot of load wear operations on that device, and that can ultimately result in problems down the road. So,
Do you have an idea of number of drive writes per day in your system?
in this case, well, I'll talk about checkpointing a little bit later. So, you were talking about general overall load?
No, if you were to deploy this,
Mm-hmm.
drives are available in a large range, let's say, of drive writes per day,
Yep.
which indicates over provisioning somewhere behind the scenes.
Yep.
I was just wondering if you had characterized the number of drive writes per day that might be typical for this type of device in this application.
So not to jump ahead of it, one of the findings was that it's very easy to exceed the rated I/O workloads for SMR drives. And that has to be taken into account when designing these sorts of systems, in that you don't end up running the drives outside of the range recommended by the manufacturers.
So it'd be a waste to buy a drive that had more drive writes per day than the SMR device could do in I/O,
Yeah.
essentially. Right?
Yeah, but what we found is that we could in essence, we could easily build a system that you could shove data into at a rate that would result in the I/O workload on the individual drives exceeding the recommended ratings.
Right.
So more that you have to throttle the workload, on average, of course, during a day, to ensure that you stay within those bounds.
No, I was talking about where.
Yeah, that was specifically for flash. Yeah. So with today's drives, I doubt that's really a big issue, but at the time that was a real worry. So that was one of the reasons why we architected it to have an in-memory index and to periodically checkpoint the index. And I'll talk a little bit about what we did there because we think it's rather unique. Okay, so then the index information is also stored as part of every object stored on the SMR drives. And that's to enable reconstruction, because the system is able to completely reconstruct itself even if the flash drive is completely lost. Okay, so what do we do with actually laying the data out onto these SMR drives? Well, first of all, we split objects into segments. And these segments have a maximum upper bound. And this allows us to have arbitrarily large objects because they can span zones, they can even span disks. The second thing we do is then we take those fragments and we split them into, segments, and we split them into fragments. And we erasure code the data to create these fragments. So you'd have, for example, when you provision it, you might have an 18 plus 3 or 21 plus 5 or however you want that to, and then of course there's a bunch of modeling to go into failure and rebuild and recovery that allows you to determine that trade-off. But unlike traditional RAID, this is a lot more flexible. You can vary the number of fragments and the number of protection fragments fairly granularly, and we designed everything to also act as a test bed for different erasure coding algorithms. So we plugged a number of different configurations into here. What's important to note is that when we split it into fragments, we're storing those fragments that allow you to reconstruct a given segment across the same number of zones as there are fragments. So if you have, let's give an example, 6 plus 3, we're going to be storing each segment spread across 9 zones. And what we do is we have a set of zones that we call a zone set that is pre-computed before you start writing. And that just allows us to, get a segment, split it up into fragments, and we know where to write. All of the write pointers on all of the zones that are part of a given zone set all move in sync. So they're always at the same point. And this is actually really important architecturally, because what this means is that our index only has to store one zone pointer for a given segment. We don't have to store it for each zone, because every zone in the set is going to have the corresponding fragments for the given segment start at the same point. So that's a huge reduction in the size of the index. It also has a number of other advantages. So if you, for example, have a zone set 1, including, for example, as we've shown here, it doesn't show with the mouse, but in essence, zone set 1 is disk 1, 3, 6, 8, etc. And zone set 2 is disk 2, 3, 5, etc. You're in essence spreading your zone sets across a larger number of disks. What that means is that when you have faults, for example, if drive 5 fails, your number of fragments affected is, in essence, a random distribution across all of your zone sets. And what that allows us to do is very quickly identify what data needs to be rebuilt. So all we have to do is look at our list of zone sets and say, which zone sets include drive 5? Okay, well, I can throw out all the ones that don't include drive 5. Now I've got a list that I need to repair. I can go and I can select a new zone. I can add that to the zone set, replacing the failed zones on drive 5, and I can rebuild into that. So in this case, for zone set 2, which is affected, I could pick, say, drive 47 to repair into. And on zone set 3, I could pick, say, drive 6 to repair into. And one of the advantages of this is you can do all your repair in parallel. Because in essence, you can write to n drives at the same time as you're reading. Now, of course, you have to deal with read-write contention, and there's a bunch of scheduling that has to be done to make that optimal. But you can leverage the fact that you're not all trying to rebuild to the same place. And statistically, this works really well. So for example, if we look at multiple failures, here's a triple fault example. If you have 16 of 18 Reed-Solomon erasure coding in a 48 drive enclosure, even with a triple fault, 23.5% of the zone sets are going to have 0 failures in them. And 45% of them are going to have 1 failure. And 26% are going to have 2 failures. And in this case, 4.7 will have 3 failures, of which you can't rebuild locally anymore. But the point being is because you have the statistical distribution, you can prioritize rebuild. When you get to the second fault, you're going to prioritize only the zone sets that have both of the faults in them. And as we can see by this distribution, that's a quarter of your total zone sets. So you prioritize those first. You rebuild those first. And because you don't have to rebuild the RAID as an entire set, this approach for rebuilding means you can get those at-risk faults repaired quickly. So even if you have another fault relatively soon after you typically have rebuilt the ones that have dual faults, you're just down to rebuilding the ones that have single faults. You have your third fault, now you're back up to having some that have 2 faults, etc. So it gives you a lot more breathing room because it lets you do prioritization. And of course with erasure coding, because you can have larger numbers of fragments, if you have, for example, 24 plus 3, you can handle 3 faults before you have any unrecoverable data loss if it's deployed in a single system type configuration. So this kind of declustering approach It lets you do a lot more intelligent scheduling. And I think this falls out of the fact that SMR drives have zones. When you start looking at zones as your fundamental management unit instead of disks as your fundamental management unit, a lot of different architectures become clear because you're forced to work at a different level of granularity. And these zones typically are 256 megabytes and on up. These are small. You complete these really quickly on the rebuild. So it's always very satisfying seeing the rebuild statistics. Oh, it's just going through zones really fast, as opposed to your typical RAID rebuild where you have to wait, and if it doesn't get all the way done, you could potentially lose the entire RAID set. Here you know that even if something really bad happens, each time that progress bar ticks a little further, that's more data that's recoverable. Okay, so a couple more architectural elements. So remember earlier in the presentation I mentioned that we stored index information with every object we stored on SMR. Well, we include this at the beginning of each fragment, what we call a layout marker block. And as we're writing through the zone, you write your layout marker block, then you write the fragment, and then you write the next layout marker block, and then the fragment, etc. And when we fill up an entire zone, at the end of the zone, we write what's called a digest. And this is a summary of all of those layout marker blocks that are in that zone. So they're actually stored twice in each zone. The reason why we do this is because skip seeking or just sequentially reading through the entire zone to get those layout marker blocks is really inefficient. If you have a situation, and remember we mentioned that we designed it so you could lose your entire index. You have customers that are wanting this system back up. You don't have a lot of time to do recovery. You don't want that 6-hour check disk type experience. We want this system to come up from a cold, hard fault really quickly and be able to service customer requests. So by putting the digest at the end, instead of having to read the entire zone, we can just open the zone, jump to the end, and do one read to get the entire set of index information from each zone. So this kind of ties into how we do index recovery. So let's say there's a crash, just someone turns off the power and turns it back on, or our software crashes, Well, this happens all the time during development, so it's good even for developers to have this run really fast. So we just discard the index. We have no idea what the state of the index is. We could be halfway through writing a checkpoint, our index is in DRAM, that's going to go away, etc. We just say, okay, index is gone. So we recover off one of two places. If we have an intact checkpoint, we'll start from that. If we don't have an intact checkpoint, the flash is not available or whatnot, we will recover the entire index from the SMR drive. Now this sounds really scary, but here's why it's really fast. Okay, we also checkpoint indexes to the SMR drives as objects. So if I'm doing a complete bare metal restore, what do? Well, the first thing I do is I find the most recent index. Pull that into memory. Good. Then what I do is I look at any zones that have been touched past that index in time. So those zones are going to be in one of two states. They're either going to be closed, meaning they've been completely filled with data, and they have that digest at the end. Then all I have to do is open that zone, seek to the end, read that data into my index, merging into the beach plus tree. That's relatively fast. Bang, bang, bang. Just go through all my closed zones. There also may be zones that are open. Those zones don't have a digest at the end. Then I have to, skip seek or just often that doesn't even make sense. Often it's just best to just linearly read through the entire zone, pulling out the index data to bring the index up to date. When you've gone through all closed zones and all open zones that have a date beyond your latest index, your index is up to date and you verified everything, and then you're ready to just have full operations. And we were actually able to make this really fast. And that was a little surprising because there was a bit of controversy at the beginning about whether this architecture would be sufficient. But Agile, let's do the simple thing first, and then when it doesn't work, we'll then go and do it better. In this case, it actually worked out pretty well. So here's our performance for recovery. And as you can see, this is very linear. And one of the things we also found is that the more drives you add, the faster it runs, because all of this can be done in parallel. And during index rebuilding, you're just accessing the drives for read. So remember we talked about the fact the zone set, you have the fragments split across each of the drives. We replicate those, the layout markers, so therefore you can pick any drive in a zone set to recover from, meaning we can get optimal parallelism for this. So if you have 48 drives, we can be recovering 48 zone sets in parallel with zero contention at the disk level. So that just flies. Our simple non-parallelized version had linear performance as well. So as you add more zones, the time to recover is just a factor of the number of zones. And once again, this is the number of zones touched since the last checkpoint, which brings me to the next aspect, which is as you're writing in data, the number of dirtied zones is dependent on how much data you're shoving into this. So if you have a cap on how much data per day you can write, that is in effect a cap on how long it's going to take to recover from a complete cold, worst case, crash scenario. So in essence, what we found out is, and this is on a limited system, as your churn when I say limited, I mean in terms of limited in capacity. We spent a lot of time looking at amplification. So a lot of our numbers here are specifically capacity constrained because you get the worst amplification when you're getting near to 100%, having the whole system full. So the time required asymptotically approaches your worst case number because more and more percent of your system is becoming dirtied. So that's actually a good thing too, because your worst case is limited. It just the slope in real world doesn't go on forever. It tapers off. And this informs how frequently you do checkpoints. Makes sense depending on different workloads to do checkpoints more frequently or less frequently. Okay, so what about I/O? So we were able to achieve pretty much 100% of the theoretical bandwidth of the drives, regardless of the object size. And the reason why we can get such high performance, even with really small objects, is because we're aggregating them in NVRAM, and in essence flushing to disk in bulk. Now the other reason why is in a pure write workload, the head's never seeking. You're just linearly writing across the platter, and that's the optimal way to work with these disks. And it doesn't get much better than that. For random read IOs, you're seek bound. So you're never going to get better than the number of seek. Now once again, a read is you do one seek and then you read the fragments. And typically, we spend a bit of time looking at contention. You have huge objects, you have multiple writes. What we do is we will store a certain number measured in megabytes of fragments adjacent to each other to try to reduce the number of times you're having to switch your read head while not slowing down concurrent writers. And that was actually an interesting area. There's a lot of parameters here where tuning can make a huge difference between a system that doesn't run very well and a system that runs very well, and also factors into that if this were to be productized, we would have to pick a sweet spot. and tune the product to work well in that sweet spot. It could have multiple sweet spots, but it's not going to have more than one of them at the same time. When you decide to set up your system to operate, you have to pick that. And a combination of what our customers were saying and what we observed, this sort of architecture you don't want to use for small objects. We're talking like 10 megabytes plus. And you see that here. 1 megabytes, you're just not seeing the read performance. 10 megabytes, you're still seeing only half of your theoretical read performance. But once you get to 100 megs and up, we can really saturate those drives. And once again, this is all because you have to seek. Yep. These particular results were with 6 spindles, but we did tests with larger number of spindles to verify that at least we weren't hitting any bottlenecks in the I/O path. So once again, pretty trivial at that low number, but because we're not doing a lot of computation here, we also weren't saturating the CPU, coming anywhere near saturating the CPU, and that's with all of the EC computation. Question? I don't have those numbers, and we haven't published them. So most of the published data is for the smaller capacity constrained system.
So when you say seek, you really mean the distance between two LDAs?
Yes.
Physical block.
Yes. Yeah, I mean, pretty much any time you have to make that, head move in the way that it doesn't want to, you're going to pay a huge penalty. So once again, this is warm. You have latency before first byte, and you have latency if you're throwing at it your nasty random read workload. But that's okay. That's okay. There's a segment of the market where this is where 100 megabytes is small, and a lot of times the bigger systems above that are doing some degree of coalescence anyways. Not that necessarily helps you when they're trying to do a seek within an object and read a range. You get back to the same problem. Okay, so with respect to amplification, write amplification is a big concern, especially with SMR drives, because once again they're rated for a certain amount of I/O per day that works out to a limit on the total I/O over the lifespan of the drive. And we wanted to make sure that we weren't we could ensure that this has a long lifespan, because when a customer buys a drive, they want it to last for a long period of time. And if we could demonstrate that we could say half your write amplification, that potentially doubles the theoretical lifetime of the drives. So we found out that, as expected, the smaller the object, the higher the amplification. But we were able to demonstrate a relatively low write amplification. So this is with a workload and there's more details on the workloads in the actual paper, where you're picking a random object, deleting it, writing a new object, picking a random object, deleting it, writing a new object. So if you think about these SMR zones, you can't just go back and delete an object. You have to add an entry saying that object back there that I'm not touching is now deleted. And then you have to do garbage collection. So garbage collection involves identifying a zone set that has lots of fragments, lots of holes, and reclaiming that. You have to migrate all of the existing objects off to another zone set, and then you can do a trim on all of those zones that correspond to that zone set, release them back into the pool to be allocated to other zone sets. So these particular results show the write amplification in the system when it's 70% full, 80% full, and 90% full, with various object sizes, including a mixed, which is the same number of objects of each of in the distribution. And as you can see, the dashed line is the theoretical write amplification, and we included your data protection overhead. So if you have, your erasure coding, that is a form of write amplification. Even with very small objects, when your system isn't completely full, you get a very low degree of write amplification. And for big objects, you're starting to approach your theoretical limits. And to note, this is when you're deleting. A lot of customers that use these sorts of systems rarely, if ever, delete. So this is truly kind of worst case scenarios given typical customer workloads. So what were the lessons learned? Well, the first lesson learned, probably something everyone here knows, is parallelism is critical, especially in these sorts of environments where you're going to have lots and lots of spindles. Make sure you design for your I/O parallelism and seek parallelism, because there's a limited number of seeks per spindle, and if you don't use those judiciously, you're going to be running at a fraction of the performance for something that's optimized for parallelizing seeks. And this is one of the reasons why we duplicated certain information. That adds to our write amplification. But sometimes by writing a little bit of extra information across multiple drives, we could dramatically increase our parallelism. Second, data spreading is critical for fault tolerance. We all know this, RAID, etc., but it's just something you have to do. The optimal zone set width changes based on the number of drives. So if you have a server with 24 drives, you're going to have a different optimal width than a server with 96 drives. That was another finding. And the use of flash for things like index and metadata, etc., dramatically improves your performance while reducing your complexity. So those are general. What about things specific to SMR? Well, the append-only model we found allows you to simplify your implementation and increase your write performance. If you can keep that head on track and just append, just write the data, it's going to go really fast. The second thing is that, people don't like NVRAM, but having it there really is good to reliably buffer the data. And while you can do things to get around that, we ended up at the end of the day saying, this is an important architectural component and it really needs to be there. Otherwise, you have to push complexity all the way back to the client. And the other thing we notice is that the SMR write performance is often significantly lower than the SMR read performance. This is different depending on your drives, but always recommend whenever you get drives, run bare benchmarks on them, characterize them, get an idea of what their read performance, write performance, and how those change when you're from your inner cylinder to your outer cylinder. And sometimes that can drive your tuning parameters. Having a system that automatically characterizes drives and then tunes itself to those drives may be a good way to irk another 10, 15% performance out of a given piece of hardware. And then finally, it's really easy to exceed your SMR disk workload limits. So the big takeaway from that is, if you're building an SMR-based system, don't optimize to try to get the highest performance you possibly can. Optimize to get the performance that the drives can handle, to be able to burst, to be able to achieve that performance during rebuilds, and then any extra overhead you have, use it for other things. Because you'll get way more value at the end of the day rather than trying to just pound those drives into the ground, because you will.
You haven't mentioned anything about the size of the zones. Do they have to be the same across all drives?
Yes, they do.
And have you encountered differences between manufacturers in that?
Not at the time we were doing the work. There's zone sizes were reasonably consistent, and we'd imagine that if you had a situation where a new set of drives had a larger zone size, they'd probably be in a larger drive and you wouldn't be mixing those. Oh, but that is an important point. This architecture lets you mix drives of different physical sizes, capacities. The zones have to be the same size, but you can mix drives. So one of the issues with RAID is you have to match up all the drives. With this sort of declustered approach, you can mix and match and use whatever new replacement drives come in, and the system will just take advantage of that within reason.
So on larger drives,
Correct. Yeah, and there probably will be a point where everybody says, I think we should double our zone size, but right now it hasn't been a big deal.
It would be interesting to know if there is an optimal zone size. You should tell the district managers what to do in that case.
We didn't observe any situations where we were complaining about that. So that's the quick presentation. So more questions?
Yeah, you said you did something to get your 1 megabyte blocks in the same zone to try and get them all together. What were the factors that you looked at beyond technical locality? What was it that you used to drive the 1 megabyte?
So the question was, what did we do to try to keep things together when we're talking about, remember we had objects being split into segments, in essence putting a maximum cap, and then we took the segments and we split them into fragments. So the segment size determines the fragment size, and then when you have multiple fragments located adjacent to each other in a given zone, that corresponds to multiple segments being adjacent to each other. So we determined that there was, an optimal segment size, and that drove our fragment size. And we had the scheduler decide the number of fragments it would lay out before it switched to another write based on TCP/IP buffer sizing. Seriously, because
That's the client.
yeah,
That's the client request, right?
yeah, because if we switch with too big of, if we make our number of adjacent frames too large, the buffer overflows, you end up getting back pressure down to the client, your performance collapses. If you make it too small, on reads, you're seeking all over the place. And remember, this is permanent. Anytime you get penalties every time you read that object. So we found that you figure out what the concurrency you're going to expect. If you have 10 clients writing to this, you look at how much buffer do you have, times the number of TCP/IP streams. That gives you an idea of about how much data you need before so you can drain them all out. And ultimately, that's what you want to optimize for. Question? That's correct. We did not use the conventional zone because when we originally started working with it, that hardware wasn't available. And later on, when it became available, we looked and said, everything we would use a conventional zone for, we just use Flash for. Yeah. Yeah. Question?
So given some of the rebuild characteristics that you get out of zone sets, does it make sense to apply some of those constraints on a flash array?
Potentially, but the flash arrays have very different characteristics. They don't have the seek limitations that disks have. They have way higher IOPS. And if I were to design, and our team were to design a flash-based system, it would look very different from this. Having said that, the concept of managing data for rebuild in zones is a technique that systems may want to apply to flash-based systems. Ultimately, we always have a challenge in the industry of dealing with things when their count gets into the billions. The example I give is the amount of time it would take to copy the contents of a volume by dragging and dropping in the file system versus the amount of time it takes to copy that same volume as a VMDK, for example. If you can take a bunch of things and treat them as a container, everything's going to go faster. So being able to do rebuild on a zone basis is way faster than doing rebuild on an object basis. And one of the reasons why rebuild flies on this is we never have to worry about objects. Rebuild doesn't even have any awareness of objects. It does the EC rebuild on the zone set basis, and never has to look at the index and never has to look at the individual structure. We in fact had completely different subsystems. We're changing the structure of how data is laid out in a zone without having to change how rebuild's done because it's opaque. It's just EC encoded. Okay, so any other questions? I'm a little behind schedule, but thank you very much for staying.